think we have an interesting panel discussion here today about a technology that I think is going to be pivotal going forward to the modernization of the electric grid in California. I want to kind of step you down in this panel into a much more practical world where what we're trying to do is actually respond to the fact that we've already pretty much failed in attempting to forestall the impacts of climate change. Climate change is here, and what we're talking about now are ways in which to deal with climate change, in my view. It could get a lot worse if we don't do the things that you're talking about doing here, but it's here already, and it poses significant challenges as we stand. I just want to make a couple of comments to give you an idea of what's important about microgrids. How do I change the channel? Let's see here. I think I have slides. They should have got put in. All right, if we don't have slides, we won't need to. A couple of years ago, maybe 5 years ago, I was contacted by the U.S. Department of Energy to study the economic cost of unreliability and poor resilience in utility supply systems for the United States. And one of the things that became really clear to me right away was that the resilience of the electric system is only a small component of the problem of resilience that communities face generally. In fact, if you look at all the impacts that we're trying to deal with in the context of what might be called resilience problems, they're really problems that arise out of the fact that electricity isn't supplied to fundamental functions inside the communities of interest. So, for example, public safety, public administration, waste management, water supply, communications. These are fundamental elements that of the organization of modern industrial societies that must be supplied in order for those societies to continue to exist. And when you deprive the communities of the electricity that's necessary to meet these fundamental needs, you can have very serious problems. I would call your attention very quickly to a very interesting and short article that you should probably read, which is called Quick Response Research on the September 8th, 2011 San Diego blackout. The reason I would have you read that is that it has a very interesting example of what can happen when you just take away the electricity. Most of the time, we have catastrophes, social catastrophes involving resilience that result from environmental catastrophes like storms and earthquakes and things where the overall insult is so serious it's difficult to separate the effects of electricity deprivation. The interesting thing about this article is it's just the electricity that's gone, and it describes essentially, like a natural experiment, what happens when you take away the electricity. Now, microgrids are an important component of supply of overcoming this, what I'll call a variety of resilience problems that emerge when electricity is supplied. Because if you target them strategically, you can put them in places where they sustain the community, where they hold it together. You can see that a lot of federal policy regarding microgrids has pointed money at military installations. Do you have any guess about why that might be the case? Because they are the last defense. Okay, and we are making sure that the military establishment continues to exist no matter what else happens. We can go farther than that and provide much more resilience to communities than simply military defense. Now, what I'm looking for the panel to do is give us a very interesting discussion of how microgrids work, what they are, and their current state of development. I'm going to start with Stephen Strong. Stephen is acknowledged as a preeminent authority on the integration of renewable energy systems in buildings. I hope he'll show you why it's so important that microgrids involve renewable energy systems and the issues associated with integrating with them. We'll follow that with Dr. Manuel Avendaño, right? Yeah, I knew I would get that. He's a senior engineering manager of emerging technologies evaluation for Southern California Edison. For those of you that don't know, this is a very important man. This is a guy that actually is deciding what's going to fit with the grid that's going to be developed in the way of microgrid applications and in the way of other renewable resource integration projects. It's a big problem from an electrical engineering standpoint that is probably beyond my pay grade to discuss, but we'll be interested to see what he has to say. And then we'll follow up with Dr. Alfredo Martinez Morales, who has already persuaded me that he is a genius when it comes to material science, and that that a lot of material science applications are embedded in microgrid applications. So with that, I'll turn it over to Stephen.
Thank you. I'm going to give you a very quick whirlwind review of a very wide variety of microgrid applications, some of which will become mainstream and some of which we hope will not need to be. This was one of our early ones, 1978. It's off the coast of Newport, Rhode Island. It was sort of an alternative to the mansions along the main ocean front by an industrialist from Philadelphia. The house had a cable from the mainland in the beginning, but during the Depression, the owner lost everything and the house became vacant and run down. It was bought by an architect couple who brought it back to life, but they couldn't afford a new cable. And so, as you can see, there's a wind turbine and solar thermal panels and solar electric panels, and they have their own little island microgrid, a micro-island microgrid. And here's the schematic. Basically, you've got solar thermal, you've got battery storage, you've got wind, and the solar thermal isn't shown here, but PV, batteries, wind, and an inverter, and also DC loads directly, because this is a very low energy, low cost, only basically 2.5 seasons, but it's been running now for 30 some odd years. The batteries have been replaced twice because they're the old scale lead acid. What it looks like, the logistics of building the project on an island, et cetera, but it's doing just fine. The next one is quite a bit out of the mainstream. In fact, forgive me for the lack of discipline, but this is batshit crazy. I came home one day and there's a tall, dark, and handsome Marine sitting in my living room. And my wife came downstairs and said, "Oh, I want you to meet Marcus. I met him at the environmental conference." It turns out that Marcus did several duties of duty in the Middle East, came back with what would now be called PSD, but instead of going down in the deep dark side, he manned up, if you will, got his PhD in environmental science with a focus on ocean engineering, and decided to make a statement by building a raft and sailing through the Pacific Gyre to get focus on the garbage bunch, the big patch of garbage. And my wife said, "And by the way, Stephen, we're going to provide his life support system. Isn't that a nice idea?" And I'm saying, got my wife aside, "Have you seen our liability coverage?" Nonetheless, he got us, forgive me for the scholars with us, but he got an old Cessna chassis and basically started to build a raft, and asked us to provide an energy system for him, which is a hybrid microgrid with a wind turbine, solar electricity, and of course power conversion to run his satellite phone, his radar and all the rest of that. And there they are, setting sail from Los Angeles to Hawaii and then on. Really crazy. The raft is made out of soda bottles. The first time I saw them, I said, you've got to be sure to glue all those caps. They didn't. So they had to go back and, but there's more to this. Of course, with a crazy story like this, there has to be a femme fatale. This woman was quite unique. She graduated Oxford University with honors, went right into a financial career, climbed the ladder, was doing very well, but was unsatisfied and basically quit her job and became an environmental crusader. And because she was captain of the rowing team at Oxford, and that's the men's and women's rowing team, decided to make an environmental statement and row across the Atlantic. Yes, and she did it. It wasn't easy. It wasn't easy at all. So when you think about all of the issues that we've got to face and all of the stuff we've got to deal with, just think about that lady. She made it to Hawaii, and along the way, there was a problem though. Her water system failed. Her reverse osmosis water system failed. She ran out of drinking water. And on the raft, they didn't know how to navigate, so they got blown out of the currents and way down south and ran out of food. She had extra food, they had extra water. They had satellite phones, they managed to meet in the middle of the Pacific Ocean and had a dinner and shared things, and then, by the way, she got there. Next one is a little bit more conventional, but not as much as you might like. This is a microgrid we did in the desert of Saudi Arabia in 1983 for Mobil Oil. And spoiler alert, there's no batteries. It's a reverse osmosis system to provide drinking water for the oil field personnel, and the storage is in fact the water, product water. Solar electricity, there is some batteries by the way for backup, but it's mainly the storage in the water itself. Getting a little bit more mainstream, we've done microgrids at the residential level for many decades. In fact, when we started in photovoltaics, you couldn't connect to the utility grid, so every system we did had battery storage. This has a dual mode system. You have, in this case, a dedicated special purpose, what we call an emergency backup panel, because you don't have to run your electric dryer when you're out of power at home, and therefore you can get along with a smaller set of batteries. It's connected to the utility. When the utility fails, there's an open blade transfer switch, which is not shown there, and they don't even know there's a power failure until the neighbors come over and say, hey, could we come in? We noticed your lights are on. They're getting a little bit more mainstream. This is commercial industrial. We did a rooftop of 1/4 megawatts of solar and about 300 kilowatt hours of battery storage for this electrical switchgear manufacturer that has plating in their facility and can't afford a utility failure because the plating system gets into a bad way. There's the battery storage, the DC to AC bidirectional inverter, and its companion climate conditioning. All of these battery systems need climate control. And this has the solar inverters also modified with software change so that they can cooperate with the battery system. And this is just for scale. Here's the Chevy Bolt just for the scale of this. Next, well, you get an idea of what it looks like. Batteries, bidirectional inverter. They have a generator on site, which they prefer not to use. Much more larger in scale and further back in time, we did this barrier island off the coast of Belize. It's an ecotourism resort. They had a utility service, but the island is very long and narrow, and the power supply is at the very south end, and as development proceeded, it was like the Colorado River as it meets Baja, California. They had 60 volts on a 120 volt line in the middle of the afternoon. They were burning out compressors and water pumps and other things. And so they put in a microgrid. This has a torque tube in the middle so that we can adjust it, not so much for performance, but because of hurricanes. And it's balanced perfectly, so all you need is one hand to move the whole thing. They had multiple generators on station. They kept them in place and in service. You have a very large battery bank, bidirectional inverter, and of course, AC distribution to the loads. Getting a little bit more sophisticated and larger in scale, this is an island in the Caribbean with a megawatt of firm power, a very sizable PV array, a very sizable battery bank, and multiple generators for backup. This is a private island, of course, that had no development and no hope of getting utility. And it's quite an interesting project. I wish I had time to tell you about the owner's idiosyncrasies. But anyway, here you have multiple wind turbines. You have a very large solar array, a gargantuan battery bank, multiple backup generators to be absolutely certain that the owner has power no matter what. The system is monitored and surveyed by satellite link, including the software review, the data acquisition, and systems troubleshooting. Getting more up to the utility scale, this is actually not a microgrid, although it could function as a microgrid. The utilities are some of our better clients, the ones that are moving forward into the future. You'll see this large solar array here. A chunk of it is facing southwest. You might ask, why would we do that? The utility asked for southwest exposure to help with their afternoon peak. And that's all about the duck curve, and you've heard enough about that. We partnered with Tesla on this project early on because they were the first ones to bring their storage to market. And it was a mixed review. Their hardware works good, but it's hard to communicate with them. The utility is using this for solar firming, peak shaving, bar support, frequency, and voltage regulation. And that's what the schematic looks like. You see the solar and the storage are both AC coupled to the grid and then right up to the substation level.
Good afternoon, everyone. Hello. My name is Manuel Avendaño, and I'm the Senior Manager at Southern California Edison. I'm part of the Transmission Distribution Organization. Within that organization, there is another division which is Grid Modernization and Resiliency. Part of that group is also the Emerging Technologies and Evaluation. It's a recently created group, and I'm here today to talk a little bit about the experience that we have had with microgrids, and just like to share a couple of slides before offer and share some thoughts, some lessons learned, some findings, and then perhaps leave more time to questions. So I would like to start with a 10,000 feet view and start getting closer to the problem. It's probably clear by now, after 2 days of conference, that California has very ambitious environmental goals that drive the policies and the programs, right? So we want to help. We want to help achieve those goals, and to that purpose, Southern California Edison, we have created Clean Power and Electrification Pathway, which is an integrated roadmap or an integrated approach that builds on those policies and those programs, and to help achieve those clean energy goals. We build on existing programs. We use existing technologies. We look into different scenarios. We try to determine what is the best way, the most cost-effective, affordable way to achieve significant reductions in greenhouse gas emissions reductions, and we want to achieve. We want to get to 80% of 90 levels by 2050. So the strategy group, a different group within the organization, look at different scenarios and how we can achieve this and determine, okay, this is what we're going to propose. So what we did is, or what we're proposing is that this roadmap is based on 3 measures, right? We're trying to decarbonize the electrical system, put in more clean energy that will make electric vehicles and electrification of buildings cleaner as well, and cleaner along their lifespan. So this plan calls for a continued carbon reduction in the electric sector, right? We want to get 80% renewables, increase also energy efficiency, or 80% carbon-free, I should clarify, through large-scale resources, but also distributed energy resources. Once we have these, cleaner, decarbonized energy supply, we're looking to also transportation sector, right? It accounts for 39%, 45% if you count refinery of the greenhouse gas emissions in the state of California. So this is an important sector to address, and to that purpose, we call for 7 million EVs, light-duty EVs, and to support the transition to zero emission in the trucks and transit options as well. So that's about 20% of the fleet in California. And finally, the third measure, which all of them are integrated, all of them depend on, are connected, and we need all of them working together. So it's about electrification of buildings. So this is in our roadmap, in our pathway, we identify that electrification of nearly 1/3 of the space and water heating in residential and commercial applications. Now, this is just there's a white paper I encourage everyone to read, published in November 2017. It's about 12-page document. It has all the details along with an appendix in terms of how we arrive to those numbers. One last comment I want to make here. It's a step into this roadmap was achieved, or we're trying to take a step in this direction with a partnership with University of California and Cal State University programs as well. And we have proposed a new pilot program called the Clean Energy Optimization Pilot, CEOP, which is designed to test new customers' programs to reduce greenhouse gas emissions. It's a 4-year, $20 million program, which will provide financial incentives to these 2 universities, these 2 programs, on a pay for performance. So we're going to try to measure how many ways and how much reduction in greenhouse gas emissions these participants achieve, right? And we want to the overall goal is to pursue, sustain, and continue emissions reduction, right? So hopefully that pilot will be approved by your regulator, CPUC. Now, just a caveat here, all of these numbers that I just mentioned, all of these plans were pre-Senate Bill 100, right? So we're working on looking into how this is gonna, how this Senate Bill getting 100% renewables by 2045 is gonna impact some of the plan that we have envisioned. Okay, so getting to the 5,000 feet, getting much closer to microgrids, right? There's a lot we can talk about the main considerations from the utility perspective when deploying microgrids. There's a list there which I think these are the most important things that we either are learning, that we are developing, that we have seen, right? And there's no time to go through each of those. I like to pick microgrid communications. Utility-owned communication systems have traditionally developed to communicate and monitor and observe large-scale resources, right? So when we're talking about microgrids, it's not many of them out there in our service territory, and we need to keep optionality to and increase or enhance our communication systems to be able to talk to these microgrids, either at the point of common coupling through an aggregator, or maybe to each of these resources behind the meter, right? So that's an important consideration that we are currently working, right? Cybersecurity implications, that's a big focus for us as well. The last one, standards. I think when I go through these kind of events, when we join working groups, I don't think I see enough from standardization, right? I know I'm aware of IEEE standards, 1547.4, 2030.7, 2030.8, which both look into microgrid controllers. But I think, to the extent that we have more standardization for the operation, planning, design of microgrids, I think it's easier to integrate, right? Those are more grid-friendly microgrids. So from 5,000 feet, let's go into the ground level, right? I'm going to talk. I have only 3 more slides, and I'd like just to talk about the 3 pilots that we are working on right now in terms of microgrids. So this is a DRP demonstration E. It's a microgrid front of the meter in Mono County in the Bridgewood Valley. It's a very small serving a very small city. It's about 300 miles north from here, if I remember correctly. This is a video. I'm gonna try to explain. It's like a 1-minute animation. It's what you're seeing there. It's a control panel simulator. I love this because this was developed by our great engineers, right? I love when they own these kind of projects and they're trying to solve these problems. And this is a very creative way of trying to get things done with partnership with consultants, with other providers. So we are seeing there, it's a control panel simulator, and see if this works. So there is sensitive information. We cannot share everything. So what you see here is it's a Google Earth map of the location of the microgrid. But what you see here as a blue line is a transmission. It's a transmission line where they're connected several resources. So we have a hydro plant here, about 12 megawatts. We have a battery energy storage over here, about 3 megawatts. And then we have another 500 kilowatt solar PV plant and most of the load for this microgrid. And there is also existing solar distributed facilities. While you have pretty much all of these are just indicators, just status, is to inform and to monitor things. So on this side, this first, you will see what this is telling you is just which voltage curve or predefined curves are being considered by a set of DER, distributed energy resources, which are talking to them through 3030.5. The other one is the other set of predefined settings in which DRs which we're using the DMP3 protocol are using. And over here, we are seeing the grid status, if it's grid connected or islanded, if the circuit breakers are open or closed. Those are basically the point of common coupling with the grid. And what you're going to see is an opening of those breakers. So this is a simulation of a fictitious scenario of this microgrid. We developed this so we can work together with others outside of SCE in terms of developing microgrid controllers, the interfaces, the visualization of the entire microgrid functions. So hopefully this will work. So believe it or not, it is working. You will see a couple of X's which will indicate the opening of the breakers. There it is. So you will start seeing the low, the power flows going into the loads towards, let's call it up. And there is another sources. So the flows are going through the rest of the system, and there is intentional delays before we change the predefined settings of the distributed energy resources into islanded mode. They used to have grid connected mode settings. We are now pushing islanded mode. So that's when they start. Once they have those updated settings, we see in this screen we see all the resources coming online. Then we have the aggregated solar PV from distributed resources coming online, and that's once we have updated, once we have pushed there the curves and the settings to those resources into islanded mode, they start producing, and that's okay. The breakers have closed. There is grid connected mode now. So we're trying to get back to normal. We're trying to retrieve those predefined settings and get it back into grid connected mode. At least when the breakers opened, there was no outages because there is a hydro plant, like I mentioned, that is keeping all the is supplying all the load of that feeder, right? So I know it's doesn't provides all the details, but at least conceptually, what we're trying to see it's microgrid scenarios in one of our feeders. This is a 115 kV feeders that goes into a 66 kV substation that goes into a 12 kV substation. So when I move forward with another project, integrated grid project, there's a use case for a virtual microgrid. So this is thinking about does it have to be a disconnection, a physical galvanic disconnection between the grid and the and the microgrid, or can we make it virtual? Can we make it to a point in which there is no power flow exchange between us and a block of loads and a group of customers? It is feasible, right? So for that purpose, we developed this concept in which we use a combination of software simulations with our pre-production systems. We took a real feeder of our system and we simulated the substation, existing solar PV facilities. We added some storage. This has been deployed as part of our storage deployment program, and then we use customer, right? So what we're trying to accomplish here is can we control the battery storage so at least that section, the end of the feeder, there's no power exchange, right? So there's still connection, there's still electrical connection between the grid, serves as the voltage and frequency references, but there is no power exchange, or it's very minimal, right? So that's another we're accomplishing some of the goals that we have with microgrids, right? But without having to disconnect from the grid, right? So I think this is just another way of looking at the concepts and the functionalities of microgrids. And finally, this is an ongoing project that is expected to be in operation in 2021. It is a Department of Defense project, so there is very little information we can share at this point. But what I can tell you is this is a resiliency application. This is critical infrastructure, and we are working with Fort Irwin to develop a microgrid control, communications. I know they are working with another separately to also put a gas pipeline. So just the level of resiliency is significant, and we are also supported them through payback analysis, right? By utilizing your existing resources, fuel-based generation, and then putting a battery storage system, which is part of our deployment program as well. How the numbers look like, right? What was a payback period? That's kind of the support we can provide to customers, microgrid like this one. And with that, I just want to thank you, and looking forward to the questions.
Okay, well, thank you. First of all, I want to thank you for coming here today. Second, for sticking around And I promise I will make this short and sweet, okay? Because I know we're getting towards the end of the day. UC Riverside got into the business of microgrids about 5 years ago. For a long time, the university has been doing a lot of research, mostly in the fundamental sciences, some in the power engineering and electronics. But it was really about 5 years ago that the university took the proactive steps to create a more comprehensive and cohesive program in order to look into renewable energy, power systems, power electronics. And the very first project that we started at the university, we call it SIGI. And I'm sorry, okay, yes, you can see it. Okay. So SIGI is the Sustainable Integrated Grid Initiative. We think of SIGI as a testbed platform that we have the ability to reconfigure as is needed depending on the type of study that we're trying to do. We call it a microgrid. When you look at it, it's a 500 kW solar PV generation. We have a 200 kilowatt, 1 megawatt hour energy storage capacity through lithium-ion batteries. We got 3 independent buildings. Each of those buildings have their own segregated portion of the system. We have some ability to control some of those loads. And over the last 5 years, we have been doing a lot of research here at the university to demonstrate some of the benefits of microgrids. About 3 years ago, we took some of that research to the outworld, right, to the communities. Particularly, we developed a project at the Chemehueve Indian tribe, and this is implementing a microgrid at their community center. Now, the community center is particularly important for the Chemehueve because it acts as an emergency response center. It is central to their local life. They gather there to provide services for children, after-school program, services for the elderly, for the community at large. But particularly when they experience any type of power outage or disruptance, and it goes for more than a few minutes into hours, especially in the summertime, they all gather at the community. So the Chemehueve, they see the need of a microgrid from a resiliency standpoint. They have already a microgrid that is provided by a diesel backup generator, 175 kVA diesel generator. But through a project funded by the California Energy Commission, we were able to deploy our microgrid that basically integrates three different types of innovative technologies. So we have solar PV. We're actually looking at 2 different types of solar PVs. They're both from the company SunPower, but they're technologies that one of them was developed in-house, the other one was acquired from a company called Cogenra before they were absorbed by SunPower. The other innovative technology is the energy storage system. It is a flow battery. And the third innovative technology is the inverter. In this particular case, we call it the matrix unit. And the matrix unit allows for the integration on the DC side of the system to bring different DC sources and then optimally regulate, the energy so that we can take the most benefit that we can out of the system. Now, on this figure here, I'm showing what the microgrid looks like. So we have the solar PV array. This is one type of solar panels. This is a second type of solar panels. At the back of the building, we have this flow battery. The combination between this cabinet here and the inverter make up the matrix. And this project, it's in its early stages of validation, right? That's one of the contributions that the university provides to these kind of projects. At the university, particularly in a place like CSERT, we focus on fundamental research, or we look at the other end of the spectrum where it's basically the design, the integration of innovative technologies, and then doing some of the testing and validation that is needed. particularly because although we have big companies like ABB or Siemens and other large companies that are already deploying microgrid systems as a turnkey solutions, and then we have professionals like Steven that has been doing it for many years. When you're thinking about the integration of innovative technologies, it's a challenge, right? You need to have a body that allows for that integration, for that coordination, for that communication, for you to be able to extract the most you can out of the system in the most effective manner. And that's what the university does, right? So through this project, we're actually demonstrating those three technologies. We have developed our own control methods to get the most we can out of those assets and also to provide the most benefit that we can to the community. So now their diesel backup generator has become the backup to the microgrid, right? So we are providing the Chemehueve the opportunity to provide 100% renewable energy to supply all of the energy needs at their community center, while also allowing them to take some of those economic benefits from such a system.